In object-oriented solutions, we often package information into read-only classes, whose purpose is just to carry information from one place to another. In Patterns for Enterprise Application Architecture, Martin Fowler called these data transfer objects, though his were not necessarily immutable. And when you code them as regular classes, they require a lot of boilerplate code. In Java 14, they added record classes to automate the creation of that boilerplate code. However, there's still a lot of subtleties that you have to pay attention to in order to achieve real immutability. A data transfer object is an object whose purpose is to store information that's being handed from one class to another, or being serialized across a connection between machines. Most of the time, we need these data transfer objects to be immutable. So in order to build a data transfer object, we need instance variables that are final and whose values are assigned in the constructor, getters for those instance variables, an equals method that returns true if both objects are the same thing and have matching values in the instance variables, a hashcode method that uses all of the instance variables, and a toString that accurately describes the object. Clearly, my IDE helped me write all of that code, so I'm pretty sure it's all correct. The challenge with these types of classes is that we have to be very careful if we change the list of instance variables in any way. The IDE is not going to fix all of this code, and that can be a source of bugs. Java 14 created record classes that implicitly provide all of that boilerplate code. With this one line, I create an immutable class with these instance variables, the constructor that sets the instance variables, which is called the canonical constructor, the equals and hashcode and toString methods, and a getter for each instance variable that is just given the name of that instance variable. Well, that's pretty cool. And if I edit the variable list, all of that generated code is automatically updated by the compiler. Slick. Records are really classes, so we can add other things to them. For example, I could write my own canonical constructor, which would be silly unless I wanted to embed some validation code into it. If I build my own, its visibility can't be more restrictive than the default one the record gives me, which is public. And if I build my own, then I have to go back to worrying about changing it if I change the list of variables that the object holds. That's exactly the problem that record was trying to fix, so they gave us a better way of doing that. A record class can have a compact constructor that has no argument list at all. Notice, this is different from a no-arg constructor, where the argument list is empty. This doesn't even have the parentheses of the argument list. This is really just labeling a block of code, telling the compiler, insert this into the beginning of the canonical constructor that you're going to generate. So, this compact constructor will result in this canonical constructor. Now, if I change the list of variables in the record, the canonical constructor will be generated correctly, just like we'd want for a record class. It's important to note that the code in the compact constructor gets inserted before the instance variables get assigned, so you cannot use them in this code. Generally, this is used for error checking and conversions, so we do all of that with parameter values, and then assign the instance variables. For example, if I wanted my map name to always be in all caps, I could do this. One last thing about constructors. You can overload the constructor just like you can in standard classes. And just like in standard classes, you have to call the canonical constructor from every other constructor. The compiler will force you to adjust this list if you change the variables in the record, but at least we get a compile error to remind us about that. We said we wanted these objects to be immutable, but we have to be a little careful to make sure that's true. I'm going to use a main method to show where our immutability is weak, and then we'll fix the problems, and our output will show that we've improved things. To see the first issue, look at this use of my hand-coded immutable map location class. If I create an object using a list, I still have a pointer to that list, and I can change it. When I run this, you can see that I've changed my supposedly immutable object. That's bad. In standard classes, if you want an immutable field, either you need the type to be immutable, like string is, so I don't have to worry about map name being changed, or we have to go to some effort to make sure it's immutable. To fix the problem I just showed you, we make the constructor copy the parameter before storing it into the instance variable. Now the object has its own list, so it won't change if the original creator changes their list. See? Now my output is the same, even after the caller modifies its list. But there's another risk to our immutability. Suppose someone calls our getter, and we give them a pointer to our list. Now, can they change it too? Yes, they can. I gave them a pointer to my array list, so they can do what they want with it. Again, the solution is to give them a copy of my array list. Now no one can change my stuff. Oops, not quite. The way I copied the list was to create a new array list from it. This makes a list of objects that the first list was made of. Oh no. Now look at this. If I save a reference to one of the point objects, I can change it after we've made it an immutable map location object. That is not good. The source of our problem is that the strategy I used for making the copy makes what's called a shallow copy. The list is a new list, but the things inside it don't get copied into new objects. Just their references get copied into the new object. We need a deep copy, where the things inside the list get copied into new objects too. There are lots of ways to do that. I could do a whole video on techniques for copying objects, but I'm just going to use a simple loop. Now, when I run my tests, the runner can change its object, and the immutable map location object is not affected. Let's look at how we do that in our record class. If I don't do anything, record has both problems. Caller of the constructor can modify the list, and anyone who calls the getter can modify the list. We fix them just like we did in the class implementation. In the compact constructor, we make a deep copy of the list, and then we hand build the getter to return a deep copy of the list. So, if we're building a record and a field is of a mutable type, in order for our type to be truly immutable, we must make a deep copy of the object we are given in the constructor, and we must override the getter to return a deep copy of the object. Bottom line, Java record classes take care of building a lot of boilerplate code for data transfer objects. What comes for free is valuable, but we can also add to that functionality with compact constructors and then anything else that you can put into a class, because records are classes. If true immutability is required, and your object contains fields that are of mutable reference types, you have to be careful to ensure that immutability is really enforced.